So hello everybody and welcome to this week's SEDS online webinar. As always, we would like to thank our sponsors from IAS, which allow us to offer all of these resources free of charge. So this includes our recorded lectures, our learning tools, and even some virtual field trips. So make sure you take a look at our website to see all the new info. Today's lecture is by Dr. Alves Finotello, who is a postdoc at Ca' Foscari University of Venice in Italy. Dr. Fontanello got his master's and PhD degrees from the University of Padova. His research interests include the morphodynamic evolution of tidal channels and the networks in tidally influenced estuaries and fluvio-deltaic environments. So thank you very much for joining us today, and I'll give the floor to you.
All right, so hello everyone, and thanks for being here. Today, I'm going to show you how both natural and anthropogenic modification of the Venice Lagoon, which occurred during the last 130 years, have impact on the morphosedimentary evolution of tidal meanders. So basically, we will use the Venice Lagoon as a study case to better understand how tidal meanders evolve through time and how they respond to changes in external forcing, both morphologically and sedimentologically. Before we start, I would like to thank all the people who took part in the research that I'll be presenting today. Of course, what I'm going to show you is part of a much bigger research effort that would have not been possible without the help and the support of all these people. All right, so tidal meanders. They surely are a common feature of tidal landscapes and are important for the ecomorphodynamic evolution of estuaries and lagoonal environment because they critically control the fluxes of water, sediments, and nutrients in there. In addition, meandering influences both the planform dynamics of the channels themselves, of course, and also the stratigraphy of the intertidal platforms that is typically cut through by channels. Improving our current understanding of tidal meander morphodynamics, we think, is critical in order to define the key features that allow us to distinguish them from their fluvial counterparts, especially in the fossil record. On the one hand, this might somehow contribute to increase the efficiency of oil production processes in tidal deposits, thanks to a better knowledge of the point bar architecture and evolution. And on the other hand, it might result critical for the conservation and restoration also of tidal environments, especially in a climate changing scenarios where intertidal wetlands are being lost at alarming rates all around the world. So one might argue that, except for the bidirectionality of the flow that typifies tidal environments, tidal meanders can be considered somehow the bidirectional counterparts of river meanders. This actually seems to be supported also by field data, as I show in these pictures, from which we see that, all the relevant morphometric feature of tidal meanders, including depth, amplitude, wavelength, and curvature, tends to scale to channel width in a fashion that is similar to river meanders. Our research group has also shown that even the migration rates of tidal and fluvial meanders are quite similar if we apply a proper normalization to account for the difference in channel width. So this actually suggests that even the lateral mobility of tidal and fluvial beds expressed in channel widths migrated per year is similar. Nonetheless, we know that there are many differences between tidal and fluvial meanders, other than, of course, the bidirectionality of the flows in tidal settings. First of all, we know that flow discharge in tidal settings change frequently through time, but typically remain confined within a very well-defined range of value. Whereas in rivers, the changes in flow discharge can be quite substantial throughout the years. Also, the spatial variation of flow discharge is quite important in tidal channels and often leads to the peculiar planform morphology with a channel funnel that we see moving from the landward to the seaward boundary. Then we also know that the stage discharge relationship is different between tidal and fluvial channels, and in particular we observe that water level maxima in tidal channels typically corresponds to slack water periods, so when we have zero discharge, whereas the bank full condition in rivers also corresponds to maximum discharge and maximum velocity. In addition to this, tidal meanders are typically characterized by a high rate of mud accumulation, much higher than in river, by the presence of many lateral tributaries within the network, and also by some peculiar planform morphologies, such as these cuspate meanders, which are typically agreed to be shaped by the combined action of ebb and flood flow. So understanding the implication of these differences is critical to improve our knowledge about tidal meanders, morphodynamic and sedimentology. Today, as I said, we'll focus our attention on a meandering channel, which is named the Gaggian Channel, found in the Venice Lagoon in the Northern Adriatic Sea in Italy. Let me give you a brief overview of the Venice Lagoon. So this lagoon formed over the last 7,500 years, covering late Pleistocene alluvial deposits. And nowadays, it's connected to the Adriatic Sea through three inlets, which are Lido, Malamocco, and Chioggia from north to south. And the lagoon is characterized by a semi-diurnal microtidal regime with average tidal range of about 1 meter and peak tidal amplitude of 0.5 centimeters above the mean sea level. Since both the fluvial and the longshore sediment supply is negligible, the morphodynamics of the lagoon depends strongly on wind-induced sediment transport mechanism. So we'll get back to this later, but for the moment, let me just highlight that we have two dominant winds in Venice. One is the Sirocco winds blowing from southeast, which typically causes storm surge events because it blows along the major axis of the Adriatic Sea. So it causes quite significant setups in the Gulf of Venice. And the other dominant wind is the Bora wind from northeast, which blows instead along the major axis of the Venice Lagoon and leads to the formation of high waves, and so to important resuspension of sediment from the lagoonal bed. This figure right here shows the results of two numerical simulations that we carried out together with Davide Tognin. And on the left, we have the maximum wave height and the maximum bottom shear stress observed during Sirocco events, while on the right-hand side, we have the same variables observed during a strong Bora wind events. So we can immediately see that when Bora winds blow, we have much higher waves and more intense bottom shear stress. So the Bora wind is truly the dominant wind in the Venice Lagoon, at least morphodynamic-wise. Our study channel, the Gaggian Channel, is located in the northern part of the lagoon. It's a channel that is up to 120 meters wide. And our study area comprises these two bands right here, which are surrounded by well-developed salt marshes. The maximum depth of the channel nowadays is about 8 meters, and it receives water from many lateral tributaries, but especially from these two lateral tributaries right here that connect the channel to quite extensive tidal flats called Palude della Centrega to the north. These two tributaries are 30 to 40 meters wide and about 3.5 meters deep. We can also see that in the present day channel morphology, there is sort of a barb here detaching from the inner bank of band number 2. And this barb is located seaward of the apex of this band. The median grain size at the channel bed is about 130 microns, with cohesive sediment lower than 20% in volumes. For the Venice Lagoon in general, and also for the Gajjan channel in particular, of course, we have quite a number of data available coming from maps and aerial images, repeated bathymetric surveys, high-resolution geophysical data, sediment core logs, and also numerical modeling. So in these pictures right here in particular, I'm showing the morphological evolution of the northern Venice Lagoon, reconstructing from the available topographic map from 1811 to nowadays. In 1811, all the major rivers were already diverted outside the lagoon, so fluvial sediment supply was already negligible at this point. Looking at these pictures, actually, we can see that two major anthropogenic interventions have been put in place during the last 2 centuries. First, significant areas at the edge of the lagoon right here have been reclaimed or converted to fish farms, so especially in the last century, so they are no longer open to tides. Second, and more importantly, starting from 1887, jetties were built at the Lido Inlet to allow for larger vessels to enter the lagoon. So they were designed to actually get the inlet to get deeper. The construction of such jetties was critical for the morphodynamic evolution of the lagoon. Here in the upper left panel, we can see how the Lido Inlet looked like back in 1811. So it was a very large inlet that actually comprised 3 different major channels: the San Nicolo channels that connect the Venice city to the open sea, the Sant'Erasmo channels, the smallest one right here, and the Tre Porti channels here on the right. In this figure on the right hand side here, instead, we see the inlet configuration after the jetties were built in 1901. So as you see, the inlet became much narrower, and this northern jetties here starts to trap most of the longshore sediment transport, forming a new strand of land right here that is today the so-called Punta Sabbioni beach. The inlet configuration was further modified between 2009 and 2014 to accommodate the storm surge barrier of the Moses project, which are highlighted in yellow here. And the Moses project was, of course, a storm surge barrier designed to protect Venice from flooding. So basically, a new island was built in the middle of the inlet, reducing the width of the inlet itself. As I was saying, the construction of the jetties was critical for the morphodynamic evolution of the lagoon because it changed its hydrodynamic. So these are again the results of some numerical simulation that show the maximum ebb and flood velocity at the Lido Inlet in 1887, right before the construction of the jetties. Actually, in 1887, the northern jetties down here was already completed. So what we see essentially is that there is a kind of asymmetry in the flow field between the ebb and the flood. On the contrary, when the jetties were completed, a strong flow asymmetry emerged, with the flow field during the ebb showing a sort of a jet-like structure that protrudes well outside the inlet into the Adriatic Sea. So long story short, the jetties cause a shift to an ebb-dominated system. They promoted sediment export from the lagoon to the open sea, and overall they set a negative sediment budget for the lagoon overall. As a consequence of this sediment budget, we observe both a generalized deepening of the tidal flats area and also a significant reduction in saltmarsh surfaces through time. Again, we can observe that these processes from this image, in which marshes are highlighted in brown. So we see the extent of the salt marshes remain basically stable until 1901, when the jetties were completed. And after that, there was a significant decrease of salt marsh area from 1901 to 1932 and from 1932 to 1970. Of course, all these hydrodynamic and morphological changes impacted on the evolution of our study channel as well. Even if the overall channel morphology doesn't seem to change much through time, a careful analysis of the available historical maps suggests that channel banks were actively migrating during the last century. So we observe that there is kind of a symmetric expansion behavior between 1901 and 1938, with inner bank deposition and outer bank erosion, both upstream and downstream of the band apexes. Then from 1938 onwards, there is significant deposition only on the downstream side of this band right here, while significant bank erosion occurred along all the other banks, causing a significant widening of the channel. That is, I think, not immediately clear from satellite images. So the choice of this calendar year in the bottom row of the figure is not random, because these are the years that approximately corresponds to period in which we also have topographic survey of the lagoon available. So we also have information about channel depth. Indeed, we have bed elevation data in 1901, 1932, and 1970 derived from topographic survey carried out by the Venice Water Authority. Clearly, data from 1901 needs to be taken with a pinch of salt because we only have 8 points included within our study area, but nonetheless, we think it's a nice piece of information to have. Then in 2011 and 2020, we also collected bathymetric data using a sub-bottom profiler. And so data density for these 2 years are much higher than in previous data set, of course. But overall, we observe a tendency of the channel to get deeper through time. And, while in 1932, the bathymetry looks kind of symmetric with elongated pools in correspondence of the band apexes, starting from 1970, we observed the formation of the barb-like morphology that I have already shown you from satellite images on the seaward side of band number 2 right here. And this barb remained there also in 2011 and 2012, of course. As I said, the overall morphology of the channel didn't change much. So meander wavelength, radius, depth, and amplitude remain within a tight range of values. So the points here, the color points corresponds to the average value throughout the whole study period, and the shaded area corresponds to the interquartile range. We see that basically all the values are always within the range of variability that is typically observed both for tidal and fluvial meanders. So we have seen how the channels has evolved morphologically. Now we might be interested in understanding how it also changed hydrodynamically. To do so, we took advantage of a numerical model developed by Defina, Carniello, and colleagues throughout the years. This model is a bidimensional depth average hydro and morphodynamic model that was specifically built to solve the flow field and sediment transport processes in shallow tidal basins such as the Venice Lagoon. So besides tidal flow, the model can also account for the generation and propagation of wind waves and the related sediment transport processes, which are especially relevant in shallow tidal flats, as we have seen at the beginning of the presentation. This model was extensively tested, again, field data from the Venice Lagoon, indeed. And we have many computational grids already available, which reproduce the Venice Lagoon morphology in different years, going from 1887 to nowadays. So as a first try, we ran an hydrodynamic simulation imposing at the open sea boundary of the grid a semi-diurnal sinusoidal tide with an amplitude of about 0.5 meter that represents characteristic spring tides in Venice. So we ran the sim for all the different historical configuration of the lagoon, and we were able to investigate the changes in local hydrodynamics at the Gajam channel. The results for the Gajam channel highlight a strong increase in local tidal range between 1887 and 1901. In the same period, we also see that the flow velocity on the left and the flow discharge on the right increased as well. We see that in 1887 and 1901, the ebb and flood velocity were almost equal. The maximum ebb and flood velocity were almost equal, whereas in 1932, the ebb velocity, are higher than the flood ones. After 1901, the tidal range keeps increasing almost steadily, whereas we observe sort of a big jump both in the velocity and the discharge going from 1932 to 1970. Tides were still ebb dominating in 1970, and such a dominance reduced a bit in 2014 because maximum flood velocity increases while the ebb at maximum velocity remain constant. We have quantified the changes in tidal asymmetry using this ratio between the maximum flood and ebb velocity as proposed by Tambroni and co-author. This parameter here, which is called the peak velocity asymmetry, we think is the proper parameter to estimate tide asymmetry in channels rather than the duration asymmetry that typically controls sediment transport processes in tidal flats. So our data suggests that the tides in the Gajam channel were flood dominated in 1887. Then in 1901, we have a nearly symmetric tidal regime. And then, we see strong ebb dominance characterizing tides in 1932 and 1970. Nowadays, we seem to be back to a slightly flood dominated tide. So what's the relationship between the hydrodynamic and the morphological changes that we observed so far? Well, first of all, let me stress the fact that we see very weak correlations between bank migration and channel widening and channel widening rates. So this suggests that the bank migration that we see does not depend primarily on the widening of the channel. In fact, migration rates seems to be strongly controlled by local channel curvature in a fashion that is similar to what we typically observe in river meanders. In particular, we have migration rates increasing as channel curvature increase. And then the migration rates tends to plateau at curvature value in between 0.25 to 0.5 channel widths. So these results actually suggest that tidal and fluvial meanders have similar planform dynamics. Migration rates seem also not correlated with tidal asymmetry and with tidal prism. So in these two graphs, the temporal resolution of the black and the blue dots is different because migration rates in blue are derived from aerial satellite images, whereas the tidal asymmetry and the tidal prism are computed by means of the numerical model. So the temporal resolution is not the same, but as you see, the trends we observe do not seem to match each other. Interestingly, however, the variation in tidal prism exhibit a strong correlation with the change observed in the channel cross-section. So what we learn, especially from these two graphs on the right-hand side, is that tidal prism control the channel cross-sectional geometry, which is not a novel result, of course, and that channel curvatures strongly control meander migration, which again is not a big news either. So we still wonder what's the effect of changes in local hydrodynamics on the evolution of our study bands, especially what's the effect of the changes in tidal asymmetry on the evolution of our channels. To answer this question, we have tried to run detailed three-dimensional numerical simulation at the meander length scale by means of depth 3D. To do so, we took advantage of the results derived from the bidimensional simulation carried out for the whole Venice Lagoon in order to impose boundary condition at the seaward and the landward edge of the computational grid. The computational grid consists of about 30,000 nodes. It has 10 vertical layers. We just consider fine sand, so we ignore sediment cohesion, and we kept the channel bank fixed, and we impose a free slip condition. Each simulation lasts for 30 days, and we've also used a morphological acceleration factors equal to 24. So all the simulation begin with a flat channel bed and a channel depth that corresponds to the average channel depth observed in each year from the topographic maps. So this figure right here shows the cumulative erosion and sedimentation pattern observed at the end of the simulation. We see that there's not much going on in 1887, likely because flow velocity were not high enough to induce significant sediment transport. Then in 1901, we see deposition going on both upstream and downstream of the bend apexes, whereas in 1932 and in 1970, deposition happens always seaward of the bend apexes. Interestingly, we also observe for these two simulations here, the formation of an elongated depositional area that somehow resemble the depositional barb that we observe from aerial images and bathymetric data. Finally, in 2013, we get back to a situation in which deposition occurs both upstream and downstream of the bend apexes. This is interesting because it looks like that ebb-dominated tides, as in 1932 and 1970, promote the formation of depositional bodies only on the seaward sides of the meander apexes. We have then tried to isolate the depositional and erosional processes occurring during the ebb and flood phase. And basically what we see from these pictures is that the overall morphological contribution of the flood phase is small when the tides are strongly ebb dominated and vice versa. And this, we think, is because it's the dominant tidal phase that control the direction of the net sediment transport within the channel. So basically when the tides are ebb dominated, we are exporting sediments, right? So negative value in this graph means that the net sediment transport is directed seaward, while we are importing sediments when the flood phase is dominant. This emerges also from the bidimensional simulation, of course, in which we have a net sediment flux directed landward when tides are flood dominated. So in 1887, 1901, and 2013, and the net sediment transport directed seaward when the tides are ebb dominated. So in 1932 and 1970. Overall, our results support the idea that was first proposed by Tambroni and co-author in 2017, that depositional bodies in tidal meandering channels tends to form downstream of the bend apex relative to the dominant tidal flow. Clearly, if ebb and flood velocity are sort of balanced, we can have deposition on both sides of the pointer. So far, we have only analyzed sinusoidal tides, and we did not consider sediment transport processes induced by wind waves. Nonetheless, this graph up here shows that, the graph shows flow discharge on the x-axis and suspended sediment concentration on the y-axis, and suggests that the sediment transport regime changed quite a bit from 1901 to 1932. That is, once again, right after the construction of the jetties at the inlet. So if we consider a wave-induced sediment transport, this shift in the sediment transport regime should be even more clear. So in particular, we have simulated, again using the bidimensional model, a 10 days time span characterized by two Bora wind events the second of which is particularly intense and are highlighted in yellow. These bora wind events are highlighted in yellow here. These are the results, again, in terms of flow discharge versus suspended sediment concentration. And in all this graph, the empty dots denote normal, let's say fair weather conditions, while filled dots indicate storm events of bora winds. So back in 1887 and 1901, we see that the suspended sediment concentration did not change substantially during storm surge events compared to fair weather condition. However, starting from 1932, we see that during storm events, the concentration of suspended sediments can be significantly higher than during fair weather conditions. So these graphs suggest that wind wave-induced sediment resuspension becomes increasingly important since 1932. And this, again, is likely due to a positive feedback that are triggered by the construction of the jetties at the inlet. So, as I said, the construction of the inlet set a negative sediment budget and promote the erosion of tidal flats and salt marshes that we observe from historical maps. Such erosion of tidal flats and salt marshes enhance both the water depth and the wind fetch, promoting the formation of higher and more powerful wind waves, which in turn increase the erosive processes even further. And this is testified also by the increase in the bottom shear stress induced by wind waves that we observe in the tidal flats called Palude della Centega, which is located north of the Gajah Channel. So here I just show the maximum bottom shear stress in 1932, 1970, and 2013, but I think it's quite clear how much the shear stress increased through time. So if the shear stress increases, then suspended sediment concentration should increase as well. And so we should somehow see a change in the sediment transport regime of the two tributaries that connect the Gajah Channel to the Palude della Centega tidal flat. This is indeed true, as we see from this graph on the bottom right corner. In 1932, both the water and the sediment fluxes through the lateral tributaries were quite small, but in 1970s, water fluxes are quite significant, and so is the sediment load, especially during storm events, which again are highlighted in yellow. And this, of course, impact also the sediment transport regime within the main channel, the Gajah Channel. So, enhanced sediment fluxes through the lateral tributaries is likely the cause for the formation of lobate deposits here in front of the eastern tributary outflow. And we observe these lobate deposits from seismic data. We also core this deposit, which consists of massive mud that grades up into poorly laminated very fine sand. And the deposits contain scattered shell fragments and a minimum amount of plant debris. Interesting, something similar to these lobate deposits forms also in numerical simulation, 3D numerical simulation, if we activate sediment supply from the lateral tributaries. So the black line here is the channel bed at the beginning of the simulation, and the red line is the channel bed at the end of the simulation along this cross-section right here. So this actually strongly support the idea, that these lobate deposits form because of wind wave driven sediment fluxes that comes from the Palude della Centega to the main Gajah Channel. Our seismic data also suggests that the mother channel cut through lagoonal deposits to reach underlying fluvial deposits, which are likely post-LGM in age. We identified three major types of deposit. The first one is the overbank deposits that occur typically at the outer bank. And these deposits are horizontally bedded and consist of mud with fine to very fine sand laminate. Mud here in this deposit is massive and contains abundant plant debris and shell, whereas sand occurs in 5 to 20 centimeter thick, again, massive layers. Then we have the deposit associated with the barb, the depositional barb, which show internal bedding, dipping at about 3 to 5 degrees. And the sediment core in these deposits highlight a vertical stacking of mud and sand-prone deposits. And there are sandy interval consisting of plain parallel, laminating, and very fine sand with interspersed silt. Muddy intervals, however, are dominant and are mainly massive again, even though they show locally poorly preserved plain parallel stratification. Finally, the point bar deposits show internal bedding, dipping toward the channel talweg at 10 to 20 degrees, with an overall fining upward trend from medium fine sands with mud to mud. And there are also millimetric laminae of fine to very fine sand. These laminations are consistent with the accretion surfaces, suggesting that the bar accreted mainly through the progressive draping of its own slope, which is also confirmed by the dominance of muddy deposits here in the upper part of the bar. We don't observe any cross stratification in these deposits, and this likely indicates the lack of well-developed high relief bedforms. So yeah, as I was saying, all these deposits are well laminated, but there are no signs of cyclic changes in the thickness of the laminate. So in other words, we don't see any tidal rhythmites such as those found, for example, in similar point bar in the Mont Saint-Michel Bay. And if you're interested in the topic, there's a hot off the press paper led by Marta Cosma that was just published in Sedimentology about rhythmites in Mont Saint-Michel. So if you're interested in the topic, you might want to check this out. So in our study case, instead, the only clear evidence of tidal processes in the point bar deposits are these double mud drapes that we found in the sediment core. These are millimetric scale laminae that we interpret as mud settling during 2 consecutive slack water phase, potentially characterized by high suspended sediment concentration. If you are interested in this topic again, go watching the Sets Online presentation that Gino Ghinassi gave last year, in which he kind of presents several study cases that we and he in particular investigates in the Venice Lagoon and other tidal settings around the world. So I was saying that in our deposits, there are no signs of bedforms, right? Because we don't have any cross-stratified deposit. And I would like to devote the last part of the talk to tidal bedforms indeed. Overall, bedforms are quite elusive in the Venice Lagoon, especially in channels of moderate size. Within the Gaggian channel, however, we were able to identify some dunes thanks to side scan data that we collected last summer together with Ruggero Caperucci and Alexander Bartolomeo from the Maron Institute. These dunes, which appear to be nearly symmetric on average, are characterized by lengths between 3 and 20 meters, and they are 1 to 35 centimeters in age, so they are extremely low relieved. Even the lee side angle is quite small, and we think this is interesting because, you know, low angles dunes in rivers, for example, are typically thought to be formed when there is high suspended sediment load, that bypass the dune lee and settle in the trough. So in this way, shaping a sort of a more rounded dune morphology. So based on what we have seen so far from numerical simulations, we have hypothesized that the mobilization of large volumes of fine sediments during major storm events might be responsible for the scarce development of high relief bedforms. So to summarize, based on the data that we have collected, we can build sort of a conceptual model for the evolution of our study channels. So in a first phase, that is prior to the construction of the jetties at the inlet, the channel was evolving following a fluvial-like mechanism of point bar growth. In this phase, tides were of small amplitude and tidal velocity were reduced. And in addition, the wind wave-driven sediment resuspension was somehow negligible because we have very shallow tidal flats and extensive marsh area. So in the Gajan channel, the two lateral tributaries did not contribute significantly to the evolution of the main channels. Instead, when the jetties were built at the inlet, the tides became strongly ebb-dominated. So the point bar deposits start forming only on the seaward side of the inner bank, and the planform evolution of the bands became somehow asymmetric. Also, the tidal prism became larger, so the channel cross-section had to enlarge in order to accommodate larger tidal prism. Moreover, as I said, the jetties set a negative sediment budget, causing extensive tidal flat deepening and salt marsh erosion. And in this way, it increased the erosive power of wind waves and further enhanced the ongoing erosive processes. This ultimately led to enhanced sediment resuspension during storm events, increasing sediment fluxes from tidal flats to the main channel, as testified by the enlargement of the two lateral tributaries and the formation of a lobate deposits at the outlet of the eastern tributary. So to conclude, my take-home messages from this presentation are these. First, the hydrodynamic and morphological changes of a tidal basin, both natural and man-made, can have deep impacts on meander morphodynamics, mostly by inducing changes in local tidal asymmetry and the related sediment transport regime. Also, wind wave-driven sediment fluxes from, for example, major lateral tributaries that connect channels with wind wave-exposed tidal flats can critically affect sediment transport regimes and also the meander morphosedimentary evolution, even in channels that are otherwise sheltered from the wind actions by the presence of the salt marshes, such as, for example, the Gajan channel. So in particular, we think that the mobilization of large volumes of sediment during major storm events, Bora events in this case, is responsible for the scarce development of high relief bedforms. And this also hinders the accumulation of deposits, sedimentary deposits, recording typical tidal cyclicity, which is commonly well documented, where accretional rates are larger than those that we observe in Venice. And that's it, I guess. Thank you very much for your attention, and of course, I will take any questions.
All right, thank you very much, Albert, for a great presentation with some very beautiful diagrams in there. So we already have a question here, so I'll read them in the chat. If anybody has any questions, please feel free to put them in the chat now and make sure you make them visible to everybody and tell us who you are and where you're watching from. So this one is from Jacko. He says, nice talk, thanks. And he's got two questions. He's from Wales. He says, what are the consequences for Venice of the most recent change from ebb to flood dominance? Is it good or bad in the long run? That's the first question. And the second question is, how do you expect the numerical predictions to change if physical and biological bed cohesions are included?
All right, so these are both very interesting questions. The first one, what are the consequences for the recent change from ebb to flood dominance in the Venice Lagoon? What I can say is that, you know, we have somehow already discounted the morphological effects of all the man-made intervention that were done in the past. So the lagoon is still exporting sediments, but is somehow closer to sort of a quasi-morphodynamic equilibrium, especially if compared to what we had back in the 1930s and 1970s. Unfortunately, because of the morphological structures of the inlet, with the jetties protruding into the Adriatic Sea, no sediment transport can actually enter the lagoon. And as I said during the presentation, we don't have fluvial inputs either. So, you know, we still have a negative sediment budget overall, but, you know, on the long term, the most recent modification of the inlet should somehow slow down the morphological degradation of the lagoon morphology. And instead, regarding how do you expect numerical prediction to change if physical and biological bed cohesion are included? Okay, I forgot to mention that, and this is actually a very on-the-point question. The B-dimensional models is actually able to include for the transport of both cohesive and non-cohesive sediments. We didn't include sediment cohesion in the 3D simulations because, you know, overall the volume percentage of cohesive sediments in the channels are small, right? So at the bottom of the channel we have mostly fine sands. What I would expect if sediment cohesion was included in the 3D runs is somehow a slowdown in terms of morphological adjustments of the channel. But, you know, we are confident and that our simulations somehow capture the relevant morphodynamic of the channel, also because we can somehow compare the simulation with what we see from historical topographic maps.
Very interesting. I was going to ask the same question about sediment cohesion, but I have another question for you while we wait for some more questions to come up into the chat. Have you compared your study site to other areas that have been modified by jetties? Is there much of a difference in what you see in the morphodynamics?
Actually, no. Actually, no. And, you know, probably I put too much focus on the jetties here, but, you know, I think that the comparison we should make is with other systems that are somehow sediment starving. So the Venice Lagoon is starving because the river were diverted back in the days, and the jetties prevented sediment import from the longshore currents. But, you know, I mean, jetties are critical just for the Venice Lagoon, but imagine you have another lagoon where you don't have active longshore sediment transport for some reason, for example, because of damming of the major rivers, and you don't have active fluvial sediment input either. I mean, that would be a nice comparison to draw, even, as I said, if you don't have jetties in there. Anyway, to reply to your question, we didn't try to actually compare. Marta Cosma and Gino Ghinassi did some work on completely different macro-tidal settings in the Mont Saint-Michel, as I mentioned in the presentation. But, you know, in terms of comparison, we didn't do any with other systems similar to the Venice Lagoon. All
right. We have another question from Claire in Newcastle. She says, cool talk. I guess the impact of the jetties could also be considered similar to the formation of a natural barrier spit in the wave and tidal systems. Since these barriers usually occur during transgression and could form relatively slowly, do you think quick formation of the jetties would force the system to respond differently as the jetties are created rapidly?
This is an intriguing question. I suppose yes. The answer would be yes. Even though, well, actually, you know, when the jetties were built, we saw that, you know, the hydrodynamic adjustments were rapid, but the morphodynamic adjustments took let's say some decades to complete. So I guess it depends on where you look at the problem from. If we talk about the hydrodynamics, then of course the quick creation of the jetties, as it happened in the Venice Lagoon, is different from the slowly evolving barrier speed in tidal system. But in the long term and morphodynamic wise, you know, of course the adaptation timescale would be different, but you know, on the long term, I would expect the overall morphological effect to be similar.
Very interesting. Our next question is from Stephen in Wales. Is anyone carrying these modeling scenarios into 100% anthropogenic settings? I'm thinking about the man-made channels or island systems off coastal Middle East and Asia.
I'm afraid I don't have an answer for Stephen. As far as I know, nobody's doing that. But you know, I might be entirely wrong. So what I can say is that one of our most active research branch at the moment is to investigate how the lagoon closures operated through the Mose floodgates will impact on the morphodynamic evolution, especially of tidal marshes and tidal flats. But you know, in terms of other areas around the world, I'm afraid I don't know anybody who's doing that. But if there's somebody that is working on this topic and is willing to collaborate, of course we are more than open to new collaboration.
Excellent. Maybe a new research area you can go into.
Yeah, why not?
All right. So it looks like we're going to start wrapping things up. So thank you very much again for your presentation.
Thank you.
And join us all next week for the seminar at our regular time, 4 p.m. UK time, when Paul Wright will be talking about carbonate diagenesis. So hope to see you all there.